Welcome back to Unit 3. We will discuss a little bit more on which visualization to choose for your data. So we already discussed sort of one-dimensional chart types where you can always visualize one aspect of your data. That's called univariate. However, especially in a scientific environment, we very often deal with more dimensions. We deal with having to visualize several aspects per data set, etc. So we will now look a couple of more visualization types that are maybe more suitable for a scientific environment way to visualize actually complex data. So one very common problem that people want to visualize is to show overlaps between data sets. So let's assume you have you look at supermarkets. Each city in Germany has probably an Aldi and a Lidl, but many cities also have local chains that are local chains or shops that are owned by individuals. So, for example, if you now track in 3 different cities how many supermarkets are common across these cities in Germany, you can make a list for Berlin, for Munich, and for Dresden, for example. And the list obviously gets very long, and some of the items will be the same, and some of the items will be specific to that city. So what you then use to visualize such a comparison is something called a Venn diagram. So here what you do is that depending on the number of items in your list, you encode the number in the area of a circle, and it's important that this is the area and not the diameter. The diameter sort of distorts the relative size difference. So once you have now bubbles of different size that represent the units in your data set, you can then analyze the overlap and visualize it by making a Venn diagram which all the different overlapping possibilities are possible. So for example, the green and the magenta have an overlap of 2, the green and the blue have an overlap of 4, and all of the overlap of all 3 cities is in this case 5. These are totally imaginary items and data. So a slight alternative possibility, and that's actually the true Venn diagram, is that you do not encode the size of your data set in the area, but you simply use 3 circles of the exact same size to only visualize the potential overlapping categories. And even if the overlap is 0, you still display it, but put a 0 in this. So why do I show this example? Because first of all, it's something that comes up in every single course that I give, and also because very few people know that the limitations of Venn diagram. So each chart type that we have, you should familiarize yourself with the limitations. So Venn diagrams are fantastic for showing the overlap across 3 different data sets, but they completely stop working if you have more than 3 data sets to compare. So there's not a single way of arranging 4 circles to display all possible overlapping categories. You can try it out at home, or you can read the very long Wikipedia entry on this. But basically what you then have to do is to change the appearance. So you have to go from a circle to an ellipse. So with an ellipse diagram, so Venn diagrams stop working for more than 3 categories. So an alternative is to make a Venn diagram with an ellipse. So with an ellipse, it becomes possible to visualize the overlaps of many more different data sets. In this case, I'm showing you all possible overlaps between 1, 2, 3, 4, 5 categories. You can see that it's still possible to read it all off, although it becomes quite tedious if I would now ask you right away what's the overlap between the green and the yellow only. You would probably have to spend now some time, go really close to the screen in order to actually read it, etc., etc. So it's time consuming. An alternative that people use and that I would really try to advertise for you to never use is to not use ellipses but bubbles. So any kind of distortion from an easy shape such as a circle or an ellipse makes it a little bit harder. So here we have an avocado shape or a pear shape, and it's already a lot harder for the eye to kind of track where the boundaries are in order to be able to read, for example, in this case, what is the overlap between the brown and the green only. So then you have to like trace the brown category like this in your mind, and trace the green category like this in your mind, and sort of see where, probably here, no blue, no red, and no yellow is interfering. So there's no items that are exclusive between the brown and the green category. Again, this takes quite a lot of time, but there are worse possibilities to visualize this. So this, I cannot even explain what kind of shape this actually is. How many categories are visualized here? Have a quick count. It takes long, and I had to be very careful. It's actually 6 categories that are visualized in this case. So here, again, no ellipses are used, but also no pairs. But instead, each category or each data set got its own shape. And now that allows you to go beyond even 5 categories, but it makes it for your audience extremely hard to tell any of them apart. So basically, the grape is sort of like a flower shape, so you can trace it back here. It's this green that goes in and out and in and out. The coffee is sort of this rectangle over here. The arborella is sort of the rectangle over here. And then it gets quite difficult. So the pine tree is this one, etc. Right? So you can see how it gets infinitely more complicated the more categories you try to display. And if I now ask you to say which category has the largest overlap, or which 2 categories have the largest overlap, you would probably end up writing down the numbers and making a list yourself. Which is why 2 years ago, Niels Gildenburg lab at Harvard, the MHD, has invented sort of the upset plot, which allows you to visualize the overlaps in data sets for as many categories as you want. So in this case, this is the overlap of something in different kind of movies. So you have romance movies, thriller movies, action movies, comedy movies, and drama movies. So these are your different data sets, your category. Here they also visualize the set size, which before we showed sort of by the area of the circle. And up here you can see the intersection size. So there's no item that appears in all of the movies, but there is one item that appears in romance, thriller, action, and comedy. A slight improvement of this kind of chart would be to flip it around. So if you flip this chart by 90 degrees, I find it a lot easier to see. And so this was just to kind of show you that there are many plot types for visualizing certain So this was just to show you that there are many plot types usually to visualize one aspect of your data. And in the end of the day, you will have to know the limitations of each one of them and sort of try it out until the message that you want to get across actually comes out. So what is extremely popular in science is to visualize distributions. For this purpose, we have something called scatterplot, bubble plot, histogram, violin, and so on. The list is probably, it goes on and on and on. So let's look at the most simple of them. The scatterplots we have usually an x and a y-axis, and we simply want to plot how different observations are corresponding to x and y at the same time. So you can imagine, for example, each dot in here is one of you guys, and I plotted maybe the shoe size and the body height, and what we can see is that there's a positive correlation between shoe size and body height, for example. However, the scatter plot is extremely versatile, which is why it's so popular. It does not allow us only to visualize your shoe size on the x and your body height on the y, but instead we can add in observations about a third dimension. If we, for example, vary the size of the data point, so the circle size. So this is what now is called typically a bubble chart, where the data are no longer simple dots, but the dots have variable size, which creates bubbles of variable size. And then we can add a third dimension of data into the size of the bubble. So now we can visualize not only your shoe size and your body height, but maybe also the circumference of your head, for example. And the scatterplots is even better than that. We can go beyond 3 dimensions and actually visualize 4 dimensions, because we can not only vary the x and the y position and the circle size, but in addition we can vary the color of the circle, or we could vary this the shape of the circle as well. And that allows us to plot yet 4th dimension, maybe your income as a student or something like this. So like this, with a simple plot in 2 dimensions, you are able to plot 4 items of data about your observed group. But here it stops. It's not possible, and you shouldn't even try to visualize more than 4 dimensions in a 2-dimensional scatter plot. Very, very often you should not go beyond 4 dimensions even with the scatter plots. But there is another limitation, and that is the number of items that you can plot at a given time. So there is a maximum number of dots that you can apply to a plot. You can show a lot in scatter plots, but not all. And to go beyond maybe hundreds of data points, you can, for example, use transparency. The problem is visualized here. So a few data points are super easy to see. You can read off each one individually. If you have a lot of data points, you can still see individual ones. At some point they start to overlap, and in the end, too many data plots just become one big plot where you can't even make out individual data points at all. So you can never go into this direction. There are too many dots that you can plot per one plot. If you use transparency, you can probably make something like this or this still quite readable. So transparency means that you do not have a dot filled with black, but the dot is maybe filled with a semi-transparent color, which allows you to see the overlap of 2 still quite easily. At some point, however, if you have too much data somewhere here, you will have to still think about somehow summarizing the data even more and not showing all of it anymore. So for a long time in science, there were these plots called dynamite plot or bar charts. So they got extremely they have a very negative perception, And the reason is that they hide more than they show. So what you can see here is that this plot only tells us the average or the mean for the category A and sort of the scatter around it. And we can, whenever there's a big error bar, we know, oh my god, there's danger ahead, something is wrong with this category. But we do not know what, because the data has been summarized.